So welcome, good morning. I'm Peter Littlewood, Director of Argonne National Lab, and I'm pleased to join you at this meeting for an announcement that has us all at Argonne very excited, and I think even some in Chicago. So I want to give a very special welcome to our three congressional representatives who are here with us this morning. We have U.S. Representative Dan Lipinski from District 3, Representative Bill Foster from District 11, Representative Randy Hultgren from District 14. As a national lab, it's our mission to provide the United States with new science and technology capabilities. And our legislators in Washington play an essential role in advocating for us and our work, and we're deeply appreciative of their support. So thank you. Joining us today, we also have Dave Patterson, President of Intel Federal LLC and Vice President of the Intel Data Center Group, and Barry Boulding, Vice President of Marketing and Business for Cray. I'm also happy to have in the audience Don Levy, Vice President for Research and National Laboratories from the University of Chicago, here with us today. Thank you, Don. And finally, a special thank you to 1871 and to CEO Howard Tolman for hosting us today. They're vital in filling a role in the business ecosystem, joining Chicago, joining the labs, joining the whole business network in a very special and new and modern and interesting way. So Argonne is the Midwest's largest federally funded research and development center. Our scientists and engineers perform research to develop clean energy, to preserve the environment, to protect the nation, and to help our economy thrive. Today's announcement is an investment that will help Argonne keep the nation at the forefront of science and technology advancement by attracting talent to the US and the Midwest, by boosting the economy, both locally and nationally, and by fostering discoveries in energy, transportation, medicine, and more. It will help us bridge the gap from ideas and technologies that will make our lives and communities safer and will lead to transformational advances in scientific research. And so with that, I would like to welcome U.S. Department of Energy Undersecretary for Science and Energy, Lynn Orr, who will make the announcement. So Lynn, thank you.
Well, good morning, everyone. It's a bit of a damp morning, but it's great to be here nevertheless. And I come bringing greetings from Secretary Moniz and the entire Department of Energy. And I'm very pleased today to announce that DOE is investing $200 million in a new supercomputer that will be located, you guessed it, at Argonne National Lab. Makes sense, don't you think? And let me also say thanks to the Congressman Foster, Lipinski, and Hultgren. It's really a pleasure to have such great champions for science and energy research here with us today. None of what we can do would be possible without the kind of support that they provide. So let me say a few words about the new computer. I know others will fill in some details. But really, this is aimed at a fundamental underpinning of really all the science and energy engineering work that we do. It will enhance our understanding of matter and help maintain U.S. global leadership in computing. The new system is called Aurora, and it's expected to be 18 times more powerful than Argonne's current Mira system. But it will only use 2.7 times as much energy. Now, this is actually important. As we make the journey toward a great advance in computing, so-called exascale computing, then we have to get the energy management part of this under control. It's not going to be okay to have a power plant located next to every computer. So that means that there's a big energy efficiency challenge that's wrapped up in everything we do. As well. So with that incredible power, the Aurora system will help us in research areas that range from biological science, material science, transportation efficiency, and renewable energy, things like flow of air around wind turbine blades, and all kinds of other applications as well. Now, there will be a second system funded with this award, Theta, and that will help us with the transition from Mira to Aurora, and it will be here next year. So over the past 2 decades, scientists and engineers have been able to use supercomputers to do all kinds of things that we now sort of take for granted. But for discovery of challenges as varied as climate change, the fundamentals of internal combustion engine efficiency, and the design of novel materials. So supercomputing truly touches everything in society. Um, if you've ever ridden on an airplane, who among you hasn't? Then so much of that is now designed using very high performance computing, and the ability to do that with trust and safety is very important. So in addition to the remarkable computing and modeling capabilities, the high performance computer will be a powerful driver for economic growth. We know from good experience that bringing together the talented people that can make this happen and connecting the researchers across the country in a scientific user facility kind of arrangement will lead to all kinds of additional activity. Chicago is already a hub for business and talent, and it's home to multiple leading research institutions, a couple of national labs, lots of industry leaders and technology incubators such as the one we're in today. And because this computer will be available to all scientific users, well, they have to write a proposal and it has to compete. And I can tell you that the competition for time in the user facilities, especially these big computational facilities, is fierce and tough. But that competition of ideas is also an important component of the way we make sure that these machines are used to the greatest effect. So let me give you a couple of examples. Here in Chicago, companies like Caterpillar and Boeing have partnered with Argonne and other supercomputing capabilities to address complicated tasks like airplane design, engine design, allowing them to maintain industry leadership and to bring new jobs to Illinois. And through DOE's SuperTruck initiative, working with the private sector, DOE National Labs modeled the airflow around long-haul trucks to reduce drag and improve efficiency. And that project so far, SuperTruck partners have leveraged those models to develop a full-scale Class 8 heavy-duty truck that demonstrated a 60% improvement in freight efficiency during initial testing. 60%. Honestly, that's a lot, and when spread across the fleet, it will make a huge difference, saving 5,000 gallons of fuel per year per truck. So if fully deployed across the long-haul fleet, operators would save 10 billion gallons of diesel fuel per year with a savings of about 40 billion in annual operating costs. So that's a pretty good return for that kind of investment in high-performance computing. And that's just one example. Industry has already used DOE facilities to improve the development of wind energy in cold climates, to model and develop high-efficiency natural gas engines for power generation, and to study chemical processes right down at the molecular level that can limit the shelf life of consumer products and control how batteries work, for example. The key promise of capable exascale computing lies in the ability to construct models that match reality in ever greater detail, and that therefore are much more accurate and predictive. And when we can predict what will happen of a physical system, then we can use that to step back and design how they will perform in the future and to investigate ideas about improvements in design way faster than you can build one and test it. So the ability to model the world in great detail is really very important, and it underlies every aspect of science and engineering. So let me finish then by saying that today's announcement will help keep the United States at the forefront of supercomputing, a field in which we've long had a lead, and but we'll have to work to maintain. 6 of the fastest supercomputers, fastest 10 supercomputers, are already located in the United States, along with more than half of the world's top 500. And that's no accident. It's the result of direct federal investments in supercomputing for science and national security, and a whole lot of work among all the people and the companies that help build these machines, and the people that help us learn how to use them, and those that use the capabilities to great effect. And so only through a strong and sustained federal commitment to the pursuit of advanced computing can we really stay ahead of other nations in this area. They'd like to compete, and one thing we know how to do is to compete, and in a positive way. So the Aurora system, along with the department's other supercomputing investments, will certainly help establish the foundation for the development of exascale computing, and we look forward to watching all the progress that will stem from that. Thank you very much.
So thank you very much. One of the fascinating things and interesting things for Argonne and Illinois, I think, about this is that it brings a new corporate partner, a pair of new corporate partners into the fold. And I now like to invite Dave Patterson from Intel Federal LLC to come and make some remarks.
Good morning, and thank you, Undersecretary Orr and Dr. Littlewood. Intel Federal is honored to be selected by the Department of Energy and Argonne National Labs as the prime contractor for the delivery of the state-of-the-art Aurora and Theta supercomputers. We're a wholly owned subsidiary of Intel, purpose-built to enable direct contracting with the U.S. government. Intel Federal consists of hundreds of engineers and specialists, and we provide the government access to the breadth and depth of Intel's capabilities in research, development, prototyping, and engineering services. The science objectives of DOE, as Undersecretary Orr covered, and Argonne are priority one for us, and we're committed to making this program a success. As prime on several DOE extreme scale research programs to date, we're very familiar with the transformative work that is being done. Coral provides an opportunity to combine expertise from Intel with our partners and Argonne to achieve things that haven't been done before. The Aurora and Theta contracts systems add to the recent selection of Intel architecture for DOE's Cray supercomputer with NERSC and the Trinity supercomputer with ACE's partners Sandia and Los Alamos. The Coral announcement marks the beginning of an exciting new future for high-performance computing. This system will attract a community of researchers and scientists to a powerful set of tools that have never been available before, with the flexibility to support their unique needs and their aspirations. The Aurora supercomputer represents a new architectural direction based upon Intel's HPC Scalable System Framework. That's a mouthful, but it's a very important term. The framework is a flexible blueprint for developing high-performance, balanced, power-efficient, and reliable systems capable of supporting both compute and data-intensive workloads. The framework combines Intel's next-generation Xeon and Xeon Phi processors, OmniPath fabric, silicon photonics, innovative memory technologies, and a high-performance software stack, along with the ability to efficiently integrate them into a broad spectrum of system solutions. The framework also provides a ubiquitous and standards-based programming model that extends the ecosystem's current investments in existing code for future generations, also very important. This framework has the ability then to scale from high-end systems to personal supercomputers and changes the paradigm from supercomputing as a tool for problems addressed by a few to a capability ultimately available to many. The Coral contract is not a destination for us at Intel, but a very important step in a long-term journey. Throughout our history, we've brought innovations in silicon architecture and software to the market and democratized them. We surpassed tera and petascale computing, and by the time we've met the challenges to reach exascale, we'll be addressing zetta and yotta scale. Intel is driving the next generation of HPC and advancing the national agenda in the quest for exascale level computing. And the Coral program is one very important landmark. It's the next one we have to reach, but it's not the end of the journey, of course. What I'm most proud about the Coral contract is the step change that it represents in terms of innovation, technology, and collaboration. We've enjoyed great working relationships with Argonne National Labs and Cray, our system integration partner for Aurora. And as we carry this program forward through execution, it's going to be very exciting to see what we're able to achieve together. Thank you.
So to continue the partnership, I'd like to invite our colleague from Cray to come and speak for a few minutes, please.
Thank you, Undersecretary Orr and Dr. Littlewood, and thank all of you for coming. Cray is very proud to be participating in this program. Cray has a heritage both in the Midwest and with the Department of Energy in providing large, very productive supercomputing systems for the use of scientists around the world and specifically in the United States in driving our competitiveness. We already have a strong presence in the Midwest. We delivered the Blue Water system in Illinois a few years ago, and we're proud to be delivering a much more powerful system for Argonne National Laboratories that will be a great step in science for the Department of Energy. We do believe at the time of delivery this could be at least one of the largest systems in the world and may well be the most productive system in the world as a supercomputer. I will say that Cray has a long heritage with the Department of Energy. The family of supercomputers that you're going to see delivered as part of the Theta and Aurora systems was first designed as a collaborative engagement with the Department of Energy in the Red Storm procurement at Los Alamos. And that family evolved over the last 15 years. And we have a code name for the class or family of supercomputer that this will be. It's codenamed Shasta. It's the follow-on to our current XC series of supercomputers. And it really is a culmination of what we see as an adaptive supercomputing vision, where a productive supercomputer has to be able to solve problems both at scale, but also to use best-of-breed technologies, both from a computing standpoint, interconnect standpoint, software. We look at systems as holistic, integrated, productive devices that scientists can use, that they can put to good use. And Shasta, the system architecture that will be the component for this Aurora system, is really a giant step for Cray. It's a giant step in our collaborations with Intel, and it's a giant step in our collaborations with the Department of Energy. We do pride ourselves in being a company of scientists and engineers. We have a huge percentage of our population at Cray are R&D, much larger than many of the other companies we compete with. And we take great pride in the applications of our systems. We have a saying that at Cray that our systems are the tools to solve the grand challenge problems of our customers. And really that's what we try to do, is provide a tool, a useful tool, a productive tool, and a complete tool from a system, software, and hardware perspective that will allow Argonne and the Department of Energy to really solve those great challenges of tomorrow. I just want to thank the Department of Energy. I think Cray has this long history, and we look forward to continuing that. We are delivering over the next few years a number of systems in the Department of Energy, and we look at the Aurora system as really the culmination of the decade and the work that we're doing with the Department of Energy. Thank you very much, and appreciate being a part of this.
Thank you very much. As you've heard, there's no such thing as a small step in computing. We only go by giant steps. But to have giant steps, you need to have bold vision, not just actually from the Department of Energy, which certainly has that, but also from Congress. And I'm actually proud that there's a real understanding of the importance of computing at this level to the national economy, to science and technology broadly, but we benefit very much from that, from the support actually of our local congressman. Argonne is lucky to have two, and a very close friend who isn't very far away, and they're all here today. So I'd like to begin by inviting Dan Lipinski to say a few words. So Dan, please.
Thank you. I want to thank Undersecretary Orr and Director Littlewood for making all of this possible, really, and also thank everyone who's been instrumental in this opportunity. Thank Cray and Intel, and also the University of Chicago. 1871. Also want to thank you for providing this this place. Last time I was standing up here, I was receiving the Champion of Science Award, and there are great things that are going on here at 1871 and making possible locally. But we need to have the supercomputing power to do so many things here locally, for our country, and for the world, to solve a lot of the problems that we're facing. We're very fortunate here in Illinois to have two of the fastest supercomputers in the world, with Mira at Argonne and Blue Waters at the University of Illinois. I was at the launch of Blue Waters just about 2 years ago. I was there, and I'm also proud to be here today to help announce the beginning of a new supercomputer project at Argonne as part of DOE's Coral initiative. We had an announcement that we made back, may have been November, December, in Washington, and at that time we were certainly expecting this and expecting this day to come. So I'm glad to be here to actually be part of the official announcement. I'm glad that DOE is continuing to push the frontiers of our nation's supercomputing capacity with Coral. Argonne, along with Oakridge and Livermore, will extend the frontier of what is possible in computing technology. Hardware alone will not develop the next generation of supercomputers. At a hearing of the House Science Committee in January, I asked about the biggest challenges facing supercomputing, and the witnesses all discussed the need for innovative architectures. Argonne will play a critical role in Coral by developing a system architecture that is different than the one used in Oakridge and Livermore. These projects are critical to American competitiveness because by building faster supercomputers, we extend the frontiers on what is possible in computing technology. That drives efforts to make processors smaller and faster and to make better use of new architectures. The benefits can be seen in the smartphones that we all hold in our hands today, that have more computational power than the fastest supercomputers did 30 years ago. It's just really amazing to think about that and think about that type of progress. What we call Silicon Valley came about because of the large federal investments in defense and scientific research, with a little help from scientists and engineers at Bell Labs. Today, computing infrastructure is just as vital to keeping our economic engines going in the tech industry. And high-performance computers also have dozens of important applications across the research, industrial, and defense sectors. Even Major League Baseball teams are now using supercomputers to give them a competitive edge. We'll see how that works this year. I'm a Cubs fan. At least we're 1-1. Supercomputers have traditionally been a strength of U.S. investment in research, but today that lead is becoming challenged by other countries. Last month, India approved a 7-year supercomputer investment that will put them on par with the U.S. and China in the race to exascale computing. While the U.S. is home to 231 of the world's 500 fastest computers, as measured by the most recent Top 500 report last November, that's down from 291 systems just 6 years ago. Announcements like today are a big part of maintaining our lead in this field, and I applaud Undersecretary Orr and Director Littlewood for their leadership and vision in keeping the U.S. at the forefront. We also need to make sure that Congress does its part in providing funding for high-performance computing projects. I helped write the 2010 America Competes Act that has increased investments in computing and elsewhere. My colleagues and I on the Science Committee have marked up and referred to the House the American Supercomputing Leadership Act, sponsored by the good friend Randy Hultgren. And this would encourage projects like these and put us on a path towards exascale computing. Fighting for increased investments for high-performance computing and other critical areas of science is going to be one of my top priorities as in the House Science Committee this Congress. And I couldn't have two better colleagues locally and with me there in Washington fighting for these. As I mentioned, the bill that Randy has sponsored, that the Science Committee has sent to the House floor. Hopefully we will be getting that done soon. And Randy has done a great job on the Science Committee. No one has done more than Randy has in promoting and pushing and helping to get the attention and getting the funding for supercomputing. And not enough can be said about Bill Foster. It's good to have him on the Science Committee now. I always say I'm just a mere engineer. Bill's a physicist, and so he certainly understands a lot more detail than I do. We all work very well together to move projects like this forward. So I'm happy to be a part of this announcement today, and I hope that DOE and Argonne, along with Oakridge and Lawrence Livermore, will continue their excellent work in this area. Our country really needs it. This is not something that is going to get to the top of the headlines, but it really should if people really understood how important this is to economic development and pushing the frontiers of science. So thank you.
Thank you very much, Representative Lipinski. That's, in fact, as you were just hearing, we're very fortunate in Illinois to have this team actually arguing for the broad science case about what we're trying to do. It's rare actually that I get in an environment like this to introduce another physicist actually onto the floor, and it may probably be the only member of Congress who actually knows how to program the machine that we're about to get. So Bill, would you like to come and say a few words? Thank you.
Well, thank you, Peter, Undersecretary Orr, and everyone for inviting me to be here today. I'm Congressman Bill Foster, and it's my privilege of representing Illinois' 11th Congressional District, which includes about the northern third of Argonne National Lab, and I believe inside that footprint will be where Aurora will be located. So, yeah, we have congressmen are like that. But as the only physicist remaining in the United States Congress, I do have a special interest in this announcement. Before coming to Congress, I worked at Fermi National Accelerator Lab for over 20 years, and so I've seen firsthand the important role that our national labs play in research and development, and seeing that drive our economy. I guess I am probably the only member of Congress who's designed 10 integrated circuits and had them all work the first time, just like all of Intel's circuits work the first time, I am sure. And as well as program vector processors. And so I know very well the trade-offs between just raw flops and communication bandwidth that are at the heart of the differences between the awards that we've been announcing over the last few months. And I'm very pleased to be at the 1871 incubator because that's also starting small businesses is very close to my heart. When I was 19 years old, our company started a manufacturing firm that makes now the majority of theater lighting equipment in the United States. So when the lights go up in the Lyric Opera or Second City or most of the lights on Broadway, 70% of the time that's our company's equipment. But at the core of our company's feasibility back in the 1970s was the Intel 8080 microprocessor. A processor, I think it was a 2.5 megahertz clock rate with an instruction rate 1/4 of that. And I think if it didn't even do one flop in an instruction, and so that it probably did, it was in the kiloflops was the range of the computing power. And so when you're talking about petaflops now, it is truly mind-bending. I'm also pleased that the collaboration involves Cray, which is one of the legendary firms. Any wonk, any computer wonk, will be able to tell you stories of the incredible things that happen on the inside of Cray machines that have just been, things that wonks would think are impossible until they find out that it actually is done routinely inside Cray machines. And so currently, Argonne is the home of Mira, one of the fastest supercomputers in the United States and the world. But just like our iPhones, the technology quickly changes and grows and needs to be updated. So high-performance computing is an essential component of the science and technology portfolio required to maintain U.S. competitiveness. Investments such as this one will lead to transformational advancements in basic science, environmental, and energy research that rely on simulations of complex physical systems and analysis of massive amounts of data. These investments will have the potential to provide countless scientific and real-world benefits. These computers can help conduct research in materials science, human health, drug discovery, energy efficiency, among many other fields. Industrial sectors, especially energy and advanced manufacturing, will also benefit from the next generation of supercomputers. Additionally, investments in our research infrastructure will provide economic benefits as they support highly skilled jobs and help grow the high-tech economy. But most importantly, this investment gives the United States a vital competitive advantages. Study after study has shown that there are few investments that our government can make that provide as high a return on investment as scientific research and development. The greatest long-term threat that our country faces on both the military and economic fronts is the threat of losing our role as world leaders in innovation in science and technology. Japan, Europe, and China already have projects in place to create integrated computational science efforts. Just to mention, computational genomics, for example, in the last few years has moved to the forefront in placing an enormous and unexpected demand on supercomputing capabilities. And actually the Moore's law for genome sequencing is proceeding faster than the Moore's law that we've seen for years and years with computers. And Aurora will help us maintain our competitive advantage as other countries are developing their own computing abilities at an ever-increasing rate. It is critical that we make investments like this one to protect our role as world leaders in innovation. And thank you all.
Thank you very much, Bill. And of course, last but not least, I would like to invite Randy Hultgren to say a few words. Thank you.
Thank you so much, Dr. Littlewood, Undersecretary Orr. Thank you. So excited to have Cray and Intel here as well, along with my great colleagues and good friends. My name is Randy Hultgren, Congressman from the 14th Congressional District. I don't know why the Illinois legislature couldn't have split Argonne into 3 pieces rather than just 2. But be that as it may, I am privileged to represent the district just west of Argonne and represent Fermilab. I am not a physicist, I'm not an engineer, I'm just a lawyer. Big question what I'm doing up here, but I believe in this country, and I believe in research, and I believe that we are at our best when we are an innovative nation, a nation that discovers, and high-speed computing is a key part of that. Speaking of not serving in those roles, I fear daylight savings time because I know I'm going to have to figure out how to reset my clock on the microwave and stove once again. Every 6 months I have to remind myself. So I'm far from being able to be able to program these computers, but I believe so strongly in what is happening there and know that this is a key time. Aurora absolutely is the next step on the path to achieving exascale computing capabilities. Argonne's next generation supercomputer, Aurora, will provide, as you've heard, 18 times the computing capabilities of the current supercomputers there. Machines like Aurora ensure that America stays at the forefront of supercomputing technology for the benefits it brings to our national security, the economy, and more broadly, our research capabilities as a nation. I also look forward to continuing work as DOE moves towards exascale. With our last Coral announcement today, I look forward to hearing about the progress for APEX, with the next step being exascale systems, hopefully within the next 10 years. My legislation, H.R. 874, which is introduced with similar bipartisan, bicameral legislation, also introduced by Senator Lamar Alexander from Tennessee, will help ensure that DOE has a dedicated source of funding for this machine. My bill would also make sure that universities are part of any collaboration between the labs and industry. an important part of this ecosystem. Few other investments have as much potential to demonstrate dramatic progress and capability across a broad range of scientific fields with real-world benefits. Just as great doctors need sharp scalpels and great artists need fresh paintbrushes, today's brightest scientists and engineers require the best tools to solve important and complicated problems. To answer big questions, we need big machines that can handle big jobs. We must also be doing everything we can to make sure that we have usable machines, which DOE has done well within the Oscar program. While China currently might have the fastest machine at this time, it's my understanding that they are not nearly as usable as our machines. It's the equivalent of having a 2,000 horsepower car that still smokes the tires in third gear. Not practical. The usability comes down to better software development and data management, but we must also ensure that outside partners have access and new students are trained with these machines. They must be up to date with the cutting edge technology so that we can finally take this knowledge to the private sector so that the United States can do better product development and testing. This is not the intent of the research, but the side benefits which we must ensure are there as well. Aurora will also benefit the private sector. Aurora will enable researchers to reimagine the design process to reduce design costs and to speed up delivery of our new designs. Aurora will allow researchers to plan quieter and more efficient full-scale energy generation plants like wind farms. Aurora will enable the modeling and simulation of gas turbine engines that are both cleaner and more efficient producers of electricity. I see it with a couple companies locally with Boeing and Caterpillar. Aurora will enable researchers like those at Boeing to model and simulate larger segments of aircraft to capture more complicated flow interactions and to make improvements without the need to build prototypes. This could result in safer, more energy-efficient aircraft. The same technology could also be applied to wind turbine blades to reduce vibration, which is a common cause of turbine failure. Aurora will also enable researchers like those at Caterpillar to reduce financial investment and cut years off their product development cycles, and will allow researchers to model alternative fuels in engines which may lead to cleaner and more fuel-efficient automotive engine designs. This is an important day, certainly for Argonne, but it's an important day as well for Illinois, for America, and for the United States, for the world as well. But I'm most excited about Illinois. I just was down at Blue Waters last week. I was down there on Thursday, being able to see what they're doing there. We have a great story to tell, and you can see it right here. This is a bipartisan effort, fighting for research dollars in Congress with the Department of Energy, with private sector, recognizing that if we are going to be a great nation, we have to be a nation that's on the forefront of discovery. And these investments are doing that, and it puts us as a state in a wonderful position to be able to say that we have two of the fastest computers in the world right here in Illinois. This is a good day for Illinois. Thank you very much.
So while we're not able to give you a piece of Argonne, we were at least to choose a name for the machine which heads out in your direction. And we're also working on getting a terabit link out so that you'll really be part of this. So thank you very much. So I think now we have an opportunity for a few questions. Brian Quirk will moderate, and I will sit down.
So actually, I'd like to add to the congratulations of everybody. Actually, I'd like to congratulate all of you for finishing on time and under budget. This is something we at the Department of Energy really appreciate. And so, gentlemen, please take note of that. Please deliver. Actually, I'm going to start the questions with so we'll have time for all of your questions. But I'm going to start one with a question about the schedule. Can maybe you guys from Intel speak about the schedule for the machine itself? Or
the development schedule will have some of my colleagues help us here with this. But first of all, the Theta system, as we've discussed, is scheduled to be it's a 2016 delivery, and then we follow in 2018 with the Aurora system. Lots of work to be done in the meantime, but but we've already begun, in fact, and we'll continue to be working on the research and development aspects, as well as the actual development of the elements of the system and then the delivery in those two time frames.
Thank you. Other questions from the floor? We've got several reporters here. Yes, please. I'm sorry. Actually.
Okay, thanks. Would one of you possibly be able to explain in layman's terms what exactly exascale computing means, and supercomputing as well, which I understand is just very fast, high-speed computing, but just in layman's terms, can we have a definition from somebody for both of these terms?
So, who wants to start?
So in terms of supercomputing, really supercomputing changes every day. So supercomputing is about solving problems that are at the cutting edge scientifically. And as the technologies that we develop advance, so do the computers themselves and the problems that we're trying to solve. So supercomputing is always, let's call it, at the crest of the wave. And so if you're solving a weather problem like you've seen back on the displays, it's about finer resolution, being able to predict new types of very complex tornadoes versus just being able to simulate a coarse-grained weather model. And so supercomputing will continue to evolve. Now that's where exascale comes into play. And so exascale is kind of the next crest of the wave. The name itself just represents a certain amount of computation. It's about 1,000 times more than typical systems that are delivered today, but it is really not about that one particular number. That's why we use the term exascale. It's about solving that next wave of scientific problems that have complexities about 1,000 times more than the problems we solve today.
So that was an excellent description, but could I just say that this is part of a larger effort. We've long had a significant effort in advanced scientific computing, and we have a big effort now to bring together teams across the agency and, of course, the national labs and all the universities and the industry partners that we work with. In exascale computing. And that's the whole milieu, the whole ecosystem of building software tools, building capabilities for using these machines, as well as the hardware designs. So we talk about this as a step along the road to exascale computing, but there's certainly much more to be done. And that's a real national priority, and it's one of the high priority cross-cutting initiatives of the Department of Energy.
Other questions? Raise your hand. We'll bring a mic to you. Sir, right here.
Yeah, what fields would benefit from this? What scientific disciplines specifically?
Pretty much all of them. But I can. It really, if you think about it, if you go to the very fundamental level, you absolutely cannot run a particle accelerator and interpret the experiments without massive computing to follow where all those particles were formed and where they went and what they did. You can't do the most detailed weather simulations that we would like to be able to do to improve the accuracy. There is huge economic benefit in being able to predict where the hurricane is going to go. That requires finer resolution than we necessarily have in the big models that we use now, although they are pretty good. If you think about the ability to get right down at the quantum level of designing new materials that have properties that allow us to make better batteries or do chemical reactions in a fuel cell or all kinds of applications there, it's so broad that you can hardly talk about it, to all the complicated fluid mechanics that move currents in the oceans and winds in the atmosphere. And then the mechanical properties of every piece that goes in an airplane, or I mean, it just goes on and on. So the ability to do predictive calculations of how things will behave can make it faster to do the building of things as we design new materials. So.
Yeah, thank you. That of course is very accurate. I'll just follow up on that by pointing out that our computing abilities have to match all of the other things that we're trying to do. So at Argonne, for example, we're working on building better batteries. In order to build better batteries, we actually have to understand what really happens inside your cell phone. And despite the fact you may think that the cell phone works pretty well, we need something which is about 10 to 100 times better. Right? So to do that, what do? We have very large other instruments that can measure the properties inside big X-ray sources. One of the things we're very proud of at Argonne is the advanced photon source, which looks inside. But that takes a vast amount of data that you then need to interpret. And so the data revolution is also paralleled by a simulation revolution that brings all of these things together. So it isn't just computing, it's how computing impacts every other area in which we try and work. As you say, from climate modeling the early universe, an expanding supernova, a battery, combustion in your engine, or making aircraft quieter as they fly in on the north side of Chicago, which is a big issue right at the moment. So we'd like to be able to do that too.
I had a question. This might be for Intel or Cray. You talked about certainly the structure and the physical computing elements and some of the power sources. Could you comment on software that's going to run these machines, and are there new techniques or new languages that might be involved, and then some of the user interfaces and potentially some of the communication pathways that interconnect? Or is this a standalone, or do these link up with Livermore and Oakridge? And
we're going to allot 45 minutes for the answer to that question. Sir?
The Aurora system will require a lot of innovation in the software stack, and it's a combination of some open source, Luster parallel file system development, and software both from Intel that exists today, some that is being developed, and also software components from Cray. One of the significant challenges in terms of taking the step change toward exascale is in areas of power, memory, and I/O. And those also have to be addressed within the software stack and elements as well. Of course, working together with Argonne, the user interface dimension is extremely important. So our software stack model is quite interesting to look at. It has lots of elements, and we have some technical folks here that can go into more detail if you'd like more specifics.
Yeah, just to add to that, of course, that's one of the things that Argonne does. Just getting a computer and parking it there, even with all of the software innovations which have been built into that, doesn't turn it into something that a user can use. And so, so Argonne and Oakridge have run jointly Leadership Computing Facility based on these two different architectures. And I should remark that actually we have IBM colleagues here in the room who are building the next generation machine, which is at Oakridge. And they've been our partners on the last generation machine at Argonne. So, so we're not dissing them, by the way, by moving from one supplier to another. It's actually part of that very interesting ecosystem. We have to be able to write codes and methods that will run on different architectures of machines, deliver them to users to solve problems that people come with us wanting to solve them. So the goal is that you don't actually have to be Bill Foster to be able to run one of these machines. You should be able to come in like Randy, I think, and actually run it myself.
I think we have time for one more question. Is there one more? Okay, one more right up here in front.
I'm just curious, a couple of folks referred to this, that this may be the fastest computer in the world when it's constructed. Is there a way to quantify the odds of that? And then I'm curious, is there a reason, is that a goal that we're striving for? Do we need this to be the fastest computer in the world? Or is it more kind of tied into how fast it needs to be for the science that y'all are envisioning with this?
Wow, another very easy to answer question. Anybody want to take a crack at it?
Several people who step up on this one. What I'll say is, from a Cray perspective, we build balanced systems for productive use. And we build a lot of them. We probably have more systems we have more systems in the top 100 than almost any other vendor. And so we know what it takes to build very fast systems and make them productive. This will be a very, very fast system, very productive. The numbers, when people classify things as the fastest, typically there's a top 500 list that's based on one little tiny benchmark, which isn't even real work. We at Cray, we tend not to use that metric as the primary metric. But if you were, I would say it probably has a chance to be the fastest in the world. We just don't know what else other people will build. At the end of the day, that's the big question. We just don't know what the rest of the world will be building at that time.
Just to add a few big numbers associated with this. By the time we get to exascale, we'll be talking about what people call billion-way parallels. So the way things get fast is by doing lots of things in parallel. Now, you can build a computer that does lots of things in parallel, but if those things are independent events, it doesn't solve problems for you. So you can produce a benchmark that gets you the world's fastest computer, but it doesn't do a useful calculation. So the answer there is that the goal here actually is to produce machines that solve problems, that solve complex problems, and the real challenges are piping this all together. And that's why we need both of these folks, actually, because the skills putting that together are absolutely critical to producing a machine that works, has value, and will solve the biggest problems, in my view. I think despite the fact that we're at the moment now ranked number 5, we still feel that we're substantially ahead of some of the ones that are officially above us in the list.
Well, let me add, I'm an engineer, so problem solving is what our real goal is. But when it comes to the politics, we want to be number 1. The USA wants to be number 1, and it's also good because I know that there's questions about, I quoted the top 500 and we've gone down in the number, and I realize there are a lot of problems with how that is done, but politically to make the point of we want to strive to be better and to get people engaged beyond the community of people who are here, to get them engaged and to try to get them to understand that this is important. So we'd like to use that, but when it comes down to it, yes, all of us here in this room understand it's about problem solving and be able to have the best that we can to solve the problems that we're working to solve.
Thank you very much, sir. A few commercials before we leave. First of all, if you get home or back to your office and forgot a detail, please don't hesitate to visit anl.gov. There'll be a banner talking about Aurora, and you'll be able to look at the fact sheet, etc. After this, we'll be happy to entertain individual interviews for any of the panelists that were here today. And please, as you exit 1871, thank you again to our fine host. If you would take a few minutes and go take a look at the television screens out here to see some of the applications, some of the science that is being done now and can be even furthered later on. Other than that, thank you very much for coming.